Chapter 13 is all about synthesis, right? And 13 goes through a lot of kind of details, but really all it's really driving at is here's a pattern, try this pattern. Here's another pattern, try this pattern. It's a little bit better than the nomenclature systems because at least in nomenclature it's just this is the answer, this is the way you do it. Did you follow the rule? No, you're wrong. So it sucks as a lecture. Synthesis is a little bit better than that because we can actually start to look at patterns. But that pattern recognition, if it's me telling you, it's obvious because you see the pattern, okay? And you know the reagents. You have to do it. You have to sit and struggle with the patterns to kind of come up with it. The idea behind this activity that you're looking at is you see all the potential intermediates, and you can start to slide those things in and out and say, well, what about this? What about this? How does this reaction work? Okay? So you need to start looking for those patterns and trying to identify them. Okay? I'm more than willing to let you guys borrow the sets of things if you want to really take them home with you, but they are posted to Canvas. Okay? So within Chapter 13, there's not a whole lot for me to lecture on because it's you working. Okay? Some of the big things I've already kind of pushed out there and asked questions when you guys were working at these. But here's kind of a list of some ideas. These are actually at the very end of the slideshow. I just slid one of them up further in it. Okay. You're usually given a reactant. What you should do within that reactant is identify where it's reactive. Okay. What are potential sites that I can do chemistry on? Okay. So if we look at the example up here, okay, there's my reactant, because it's on the left-hand side of the arrow. Where do I have chemistry? Okay. We could potentially look at the lone pairs, or the carbon attached to the bromine, or we have CH3s. Do we have chemistry on the CH3s? Ish. Why are we saying no? CH3 is relatively stable. There's not a lot of polarization there. So what we're focusing on is the polarization caused by our bromine. Okay, the bromine gives us lone pairs as potential site of reactivity, and the bromine makes the carbon positive because bromine's more electronegative. So what we're trying to do is identify where chemistry can happen. Once we have an idea of where it can happen, that limits now the amount of different things that can happen to it. Whereas if we just look at the structure, we can say, well, an oxygen appears, so I'm just going to draw an oxygen. Can't do that. You have to be able to acknowledge where those pieces are and how they shift around. You should do the same thing with the product, because you're typically given a product in a synthesis question. So we would look to the product and say, okay, where's that product reactive? Okay, we have the double bond. We have the oxygen with its lone pairs. We have the carbons attached to the oxygen. Why are they reactive? Partially positive because of the oxygen. So we're recognizing sites of reactivity and potentially how we can shift and align between these things. Okay? The next big one, which shows up a little bit less frequently, though it's supposed to be on this one, is are there constraints on the sources of carbons? So in going from the reactant to the product, sometimes you're told you can only use this reagent. Well, if you only use one reagent, it's a simple synthesis. You just do that reagent. Hey, you're done. Okay. What if we tell you you can only use 4 reagents? You have more things that can happen because now we have the potential for more reactions, but you're still only using those 4 reagents. Don't make it more complicated by going to other sources. Okay? The next big one that I've actually found I think should probably move higher up on the list is identify the changes. Okay? And we've done this in the Diels-Alder reaction in the lab. We're identifying what things happen as we go from one to the other. And in some cases it's relatively simple, and in other cases it's stupidly complex. Because if we look at this question, how many changes do we have? Looks like a lot of changes. Okay? And before we get daunted, we should just kind of go through and list some of those to try and think about that. Okay? So one of the constraints here is that your only source of carbon Any guesses? Is that starting material? Right? And the rest of the synthesis, you cannot bring in any more carbons. Okay? You can use that structure again, but you can't bring in more carbons. Okay? So in that next, well, actually, even before we do that, can we identify some changes? Do you see any big changes? What was, I think you said another one?
You gave it oxygen.
Oops, sorry. What else? We'll be a little bit careful about saying gaining sigma bonds. It's easier to reference gaining pi bonds. Gaining sigma, we should actually reference the group that we're adding. What do you mean add a methyl group? That's going to be questionable because we can only use 3 carbons as our source. If I added a single methyl, I would have had to get rid of 2 carbons off that. I can kind of accept excess. You're saying ether. You want to work on that a little bit further?
I'm just like, where the bromine leaves, you're left with one structure.
Okay, you would have an isopropyl cation if the bromine left, yep. Which is interesting because where's the reactivity? At which carbon? The central carbon. And yet when we look at our product, really we're looking at the terminal carbons being our reactive ones, not the central ones. So that's a bit odd. Okay. So what does that likely mean is happening? We are shifting the functionality from one carbon to another. Okay. How can we increase reactive carbons? There's a particular reaction that gets us more reactive carbons. Not radicals, that takes us from no reactive to one reactive. What functional group has 2 reactive carbons? There's actually 2 of them. Nitrile is a carbon and a nitrogen, but right idea. Alkenes. There's 2 carbons in a double bond.
So what you're looking at is an elimination.
So in a very good first step, I could potentially run an elimination reaction, which could then take it down to this. What does that piece look like? That's starting to look like that piece. Is it perfect? No, because I have another site of reactivity. I have that red one that I circled. So it's not perfect, but it's getting me closer. Okay? So it's starting to look for those changes and identify pieces and ways to approach it. Okay? So we can look for those changes. We said to lose the bromine, and then we just started running with what Jennifer said, and then said what looks closest to it. We need to shift the reactivity around. Alkenes work. Holy crap, an alkene actually gives us a piece that looks darn close to what we actually want. Okay. The next one in that identify your major functional groups or functional group changes is identify the carbon skeleton. Okay. This is going to become increasingly important. When you did the Diels-Alder reaction, anybody in lab lose track of where carbons were going? There's at least one hand, and I would bet with everybody laughing, I'm going to guess a lot of you lost track of where carbons were going. Is there a way that you could keep track of where the carbons are? Number them. Color code them. Okay? That can help you make sure that you don't lose carbons in the process. It can also make sure that you don't end up adding extra carbons. If we go through and start with this, our reactant had how many carbons in it? 3. How many carbons are in our product? 6. What does that likely mean? I need 2 of my reactant to go into that product. Okay? I have to look at 2 different pathways to make a piece that can then react with each other. Kind of makes sense? Okay. Last big one, do you have to move reactivity? And we actually already talked about this. As Jennifer pointed out, the bromine reactivity in our starting material is in the middle. If we look to our product, our reactive carbons are primarily at the ends. Okay? So we have to come up with ways to shift that reactivity around. That is likely going to be done through a double bond. Okay? Questions about that? Okay. When it comes to the sets, ideally, or you guys want a little bit more time to play around with that? Think you got a little bit better idea on where to go? Or you want to do that again on Wednesday? Okay, Wednesday is the verdict. Ideally, kind of group those together. Just put the little clip on that. Hopefully your name is now on that sheet, and that'll keep getting passed around. Again, ideally, everybody's name is going to end up on the sheets at the very end.
So are the questions like these going to be on the test on Monday?
Yes. Okay. What might be a good place for me to source those questions? Probably from the sheet that I'm making you do. Okay? Probably a good idea to take a look at that. Okay? I do not expect you to be figuring these out on the fly in class every single day. What I do expect you to do is spend some time looking at them at home. Theoretically, you go home and you're like, I think I got this one. You come into class, say, what about this one? And the rest of the group can look at it and be like, no, that reagent doesn't work. Sorry. Sometimes that happens. Okay? Or they look at it and say, yeah, I think that's awesome. That's perfect. I got that same answer. Okay? It is that kind of working together to look at the pieces and how they fit that you need to be working on and approaching. That's how you're going to get the reagents memorized, not by flashcards. Okay? Questions? Deep breath, it's not that bad. You already have more memorized? Okay. I'll reveal bits and pieces of this synthesis as we continue, but I'm not going to go any further with this one yet. Well, maybe we will. Okay, so we recognize that this piece is starting to be right there. What's missing? So now we have a new synthesis question. We're trying to make that piece. What is the difference between those pieces?
Reactivity on the primary carbon that's away from the carbon.
Okay. If we look at that, we have reactivity at that carbon. I need this carbon to become reactive. Is it particularly reactive right now? No. Why not?
Because it's happy.
Kind of except happy. What's the functional group?
Methyl.
Methyl is technically the classification or the further identification of this functional group. What is that functional group? It's an alkane. Okay. How do alkanes react? They don't, because there's no polarity. How do we make alkanes react? I think this group knows because we talked about it last Wednesday. Maybe? What's that? Radical reaction. If you have an alkane, you need an alkane to react, you have to do radicals. So run a radical reaction. Which one? I don't know. You figure it out. Okay. What we talked about last week was looking at activating our alcohols. Okay. And we said we can take an acid, ideally a strong acid, and react it through. That strong acid activates the alcohol leaving group to give us a good leaving group. Depending on the identity of A-, we can see different branches coming out of this. Okay. In one case, we're saying A- is it's not just that it's a nucleophile. Nope. It's a strong nucleophile. Okay. Whereas down below, I heard people say weak. Do we even know it's weak? Do we even know it's a nucleophile? We're forming a carbocation. We actually don't know much about it yet. Okay. But if we had a strong nucleophile, we could go up above. Okay. If we don't know about the nucleophilic characteristics, we're then left at this carbocation. Okay. We'd then have to evaluate A- in a little bit more detail. Okay. If we had I-, where does that classify? Strong or weak? Or strong or questionable? It is strong because negatively charged, and it's actually not electronegativity.
But it's also big.
It's big. Okay. That increases its nucleophilic characteristics. Okay. Bromide, electronegative, smaller than iodide, negatively charged, it's still pretty darn big. Both bromide and iodide are your classically strong nucleophiles that actually work out really well. Chloride and sulfate. Interestingly enough, they were added on at the exact same instant. So what might you say about their nucleophilic characteristics? Not the greatest. The chloride isn't bad, and we've used chloride as a nucleophile before, but it's not super strong. Sulfate, horrible nucleophile because
It's very big. It's too big.
it's too big. Resonance. That's actually why it's big. The electron cloud is dispersed across a very, very large structure, not across a single atom, but across the structure. That makes the sulfate so bad as a nucleophile, it does not act as a nucleophile. Okay. Chloride, kind of in a floating gray area. It is typically a nucleophile, and it can react, but it's not going to react very swiftly. So it's probably going to fall under that second pathway towards that carbocation. Okay. And we can either finalize our substitution or an elimination. What's our differentiation between the substitution and the elimination? Substitution versus our elimination. Okay, so I heard base referenced. Why did you reference base?
It's not acting as a nucleophile.
I won't quite accept that.
Because you're removing a hydrogen to disperse the
I'll accept that. To do the elimination, we have to remove a hydrogen. So that means that species is by definition acting as an acid. To make the acid react faster, we would need to add a base. So we could say the elimination, we're saying that A species is now acting as a base. But let's hold that thought for a second. Where did A come from?
from HA.
From HA. HA was an acid. So you're telling me that I'm adding a strong acid and somehow also by that same species having a strong base? No, that's not very likely.
Unless you did it in
Okay.
steps.
So the steps is always something that people like to throw in there. We wouldn't be ending at a carbocation. We would end at the halide, and then we'd be doing the elimination to the halide. Okay? So we can't say add acid, now I'm at a carbocation, now I add base. It's two separate reactions. They must be treated as such. We would get a conjugate stronger base. So let's run with that. Okay? Let's say that, I'm going to push it a little bit to the extreme. Let's say we're adding a strong base from the outset. Boom. B, base, big old negative charge. What is that base going to react with? Remember what we're trying to get to, right? And yes, that was a dick statement, but I'm going to stick with it. We're trying to get to the elimination product, trying to get to that double bond. What does that big old bulk base do? Wait, what?
Donates its electrons to the hydrogen.
No, you're fine. You're saying the electrons from the base donate to the hydrogen. But to get to the elimination, what do I want it to donate the electrons to? That hydrogen, so I can form the double bond, right? Okay. So why are you having it attack the oxygen and not that carbon-hydrogen? Because I wanted the carbon-carbon double bond.
Not the most reactive hydrogen.
Where's the most reactive hydrogen? Okay. Just because you want to eliminate the double bond or to make that carbon-carbon double bond doesn't mean the chemistry is going to allow you to do it. When you add a reagent, you have to think, where is it going to react? Well, guess where it will always react? The most reactive place. Why is the hydrogen attached to the oxygen more acidic than the one attached to the carbon? Oxygen is more electronegative than the carbon, making that hydrogen more acidic. What does that do for the sake of our reaction?
Gives us a negatively charged oxygen.
Gives us a negatively charged oxygen. Okay, well, I still have that hydrogen, right? So couldn't the base now come in and attack that hydrogen? Why not? Form the double bond and then kick out the leaving group.
Oxygen is not a good leaving group.
If hydroxide was a bad leaving group, how bad of a leaving group is O-2? Okay, it's a horrible leaving group. Okay, so when we think about our reactions from first semester, it is fine to say elimination means base, but not always. Okay, elimination means base if you have an alkyl halide. If you have an alcohol, we've increased the potential reactivity. We now have another reactive site. We have to take that into consideration when we run our reaction. How to make sense? Okay. Our primary mechanism in all of these runs along that SN1 pathway, believe it or not. We do end up forming the carbocation primarily. Okay. Not quite a pun intended on that. When might we expect it to not form the carbocation?
When it's a primary carbon.
When it was a primary alcohol. If I made those hydrogens, we would very likely see the SN2 mechanism run. Okay? Into the specifics of these, HI and HBr are stupidly strong acids, really good nucleophiles, which means those are really easy reactions. You just throw them in, we add the acid, we add the alcohol, we're good to go, we do the substitution, beautiful, done, end of the story. Chloride, if we just add HCl to it, it's probably going to take a while. Okay? That is not going to be an easy reaction to do. So this is where one of our kind of named reactions comes up. This guy Lucas came along and said, well, I want to speed the reaction up. Okay? For the reaction to go faster, what needs to happen? I need to make that leaving group even better. And he did that by adding what kind of a species? Fair enough. He added a metal. What is a characteristic of our metal? It is ionic. I will accept ionic as well. So let's take it into its formula, into its ionic formula, sorry. What else is a characteristic of that metal? Which one's the metal? Zinc, okay. Yes, what's that? Of? What is the charge on all of our metals? Positive. What is the charge that you were required, at least if you took it here, to know the charge on zinc from all of your Gen Chem classes? Zinc plus 2. What is the zinc going to act as? An electrophile. It wants electrons. Okay. Why we don't reference it as an electrophile all the way through is a good question. What we end up referring to it as is a Lewis acid, which is the same as electrophile, right? Okay. Except in this case, probably the reason we don't refer to it straight up as a Lewis acid all the way through is that what are we trying to end up with? What's our final product going to look like? What should our final product look like?
Positive charge.
Chlorine will be on there somewhere. Good. All right. Why do we not refer to it as just strictly an electrophile? Well, look at your product. What did the zinc chloride do in the course of going from our reactants to our products? What did zinc chloride do? Doesn't really look like it did anything. Okay? So it's one of the reasons why we don't reference it in that electrophile nucleophile terminology. We will refer to it as a Lewis acid because it was in... Oh, that didn't do what I wanted it to do. Oh, well. We will refer to it as a Lewis acid because it is doing chemistry. Okay? In the course of this reaction, though, it ends up getting reformed. So it is a Lewis acid while at the same time being catalyst. It helps catalyze and speed this reaction along. How? It makes this group so good as a leaving group that it really polarizes that structure and pushes us to the carbocation much easier so that the chloride can come in quicker for a better backside attack. Okay, or a better attack in general. Okay? So what do you need to remember out of your Lucas reagent? You need to remember it's a combination of zinc chloride and HCl. Which one's the big reactive one? HCl. Okay? The chloride is our nucleophile. The H is there as potentially to activate our leaving group, to give us that water as a leaving group. The other option is that that H is not quite acidic enough, and that's what the zinc chloride's there for. It's there as a catalyst in substitution of our hydrogen to make it a better leaving group, and the structure falls apart a little bit quicker, and we get to our product a little bit easier. Why is this one that gets named?
Because you worked really hard at it.
It's at the bottom of the page. It's an incredibly fast reaction for tertiary and secondary alcohols, okay? Which means if I have some alcohol and I don't know where the alcohol is located, all I got to do is add a little bit of zinc chloride and HCl. And what ends up happening is the zinc chloride hydroxide structure precipitates out of solution. Okay, so I take two clear solutions, mix them, and I see a white precipitate. What does that mean? A reaction happened. Why did the reaction happen? Well, because the alcohol was a good leaving group, which meant I formed a really stable carbocation. It gives me some classification information. I now know that whatever that alcohol was, the alcohol was located at a tertiary carbon or a secondary carbon. What if it takes an incredibly long time to run? It was a primary carbon. So it gives me information about the structure because of that precipitation. Okay? That is the reason it gets named. You can potentially see this kind of question show up on the ACS. What it's based off of is a lab will actually do known as qualitative analysis. You mix chemicals, you look for reactions. That tells you information about the structure. Why is that becoming less popular now? What's that?
So that we can just see the structure now. We take the picture.
So I can just look down and say, oh, that's the structure of sugar.
We have imaging.
What's our imaging? Close, but not quite. HNMR, IR. We can get that same structural information using a piece of equipment that doesn't involve chemicals, which means we are safer. Okay? Are the classification tests still used? Yes, because they tend to be faster, but they generate more waste, and so in the long run, they end up being more expensive. Okay? So here's some fun little stuff. We got some complications to consider within our acid activation reactions. For those of you that downloaded the slides, you probably already saw this popping up. So,
Leaving group, you have a secondary carbocation, and there's a tertiary potential there. You do a rearrangement.
Yep.
And then the bromine will come and attack that tertiary carbocation.
all right, so let's walk through this on how I would use terminology for this. I personally look at a reaction, look at the reagents, and say, okay, what's the most reactive thing? Okay, which you need to start getting in the habit of because you may not be given the products. Here I'm asking you to explain the result, okay, but you may not be given products, so you have to be able to look for something. I look at an alcohol and I look at HBr. So I could even go through and name that, but I'm not going to because I suck at naming. Some alcohol versus HBr, which I know to be strong acid. Which of those two is the most reactive thing? Which one do I not want in my face? The strong acid. So the strong acid's the dangerous one. Why is it dangerous? Salt dissociates. I don't have any problems with salt.
Hypertension's a terrible thing.
H plus. That H plus is going to melt my face off. Okay? So I want to stabilize that H plus with anything with electrons. Where do I have the most available electrons? The electrons on the oxygen. And I wouldn't say OH, because that starts to make you think it's a base, or a strong base. And it's not a strong base, it's a very weak base. I would have the electrons from my alcohol attack that hydrogen, break that bond. My OH2, theoretically, I would make sure that I was good with my charges in lone pairs. I now have a great leaving group. With all of these reagents, or all of these reactions, they tend to follow the SN1 dynamics and we form a carbocation. Do we know this reaction is following SN1 dynamics to form a carbocation? What did you say? Yeah, why? You look at the results. Okay, at this point we have bromide floating around, Br minus. We could have that hook up with a positive. Okay? It could have attacked backside attack over here. okay, to try and chase that out. Did that happen? No. Okay, and the reason we know it didn't happen is that we don't end up with the bromine at the secondary position. What ends up happening? A hydride shift. For those of you curious about the curlicue, you can ask me after class. And we end up with the bromine at the tertiary position. Okay? So it's recognizing the mechanistic steps. What are those intermediates? How does that reaction occur? Those are all things that you need to be asking as you answer a question. Okay? Because it could very easily just show up, what's the product? Okay? And if it was in a what's the product situation, more than likely we would end up with that as an answer, particularly for an ACS test. That becomes problematic. Okay, we would probably also see this as an answer. And we would probably also see something like that, because I'm out of space. Okay? What's fun about this is those middle two structures are the exact same, yet students tend to look at it and say, well, that's not the same because I did a rearrangement and I did a methyl shift, so now it's a new structure. No. Okay? So you got to be careful with those approaches and how the structure will spin, flip, or rotate. Yes?
You don't also those two structures with a stereo center?
In this case, they could give you all those answers. In which case, do we care about stereochemistry? No. Okay, so you don't have to worry about it. If stereochemistry is shown in a multiple choice test, then worry about it. If it's not, don't stress about it. Okay? The next one, what happened in the next one? Give me that a little bit better. The lone pair on the oxygen attacks our zinc, giving us a really good leaving group. Then what happens? Okay, we can get our chloride. And you're saying the chloride does a backside attack, and I don't see SN1 in this case. Why?
Because otherwise it would shift from a primary to a secondary carbon.
Let's take a step further than that. If it had gone SN1, we'd form a primary carbocation, and then you're saying, well, that would immediately shift to a secondary, but then wouldn't the secondary shift to the tertiary? So why did that not happen? I'd have to form the primary carbocation. Do primary carbocations form? No. Okay, so I can still assume SN1 dynamics up until I hit a point where it's like, whoops, that doesn't work. I have to backtrack, and how do I work from there? Okay. Next one, H2SO4, concentrated, what happened?
The hydrogen on the H2SO4 gets attacked by the O8, O, and the OH.
Okay.
And then we have elimination that occurs.
Oh, I'm pretty sure I screwed this one up pretty thoroughly, but oh well. Oh, actually, no, I didn't. I was really mean. So we could do the elimination. Where would the elimination occur?
You lose a hydrogen at the tertiary carbon. And that hydrogen, we thought would be picked up by the HSO4.
Okay, we can talk about that being a secondary issue. So if you're going to do that elimination, what did you eliminate?
Oh, sorry, the OH2 also. Am I seeing that right? No.
The OH2 is at a different carbon.
I think I didn't see the structure correctly when I went through this thing.
Okay. I think in this one I have to say dilute. So while that may act as a good leaving group, we can't pull the hydrogen from the tertiary position. We'd have to pull it from the secondary to form our elimination product. What's the issue with that product? It's in the wrong spot. What happens if we were saying dilute acid? That means we have water and acid present. How do alkenes react? is nucleophiles or bases. If it reacts as a base, it reacts with the acid. Where does the H plus go? The least substituted, and at the most substituted we have, there's no OH yet, a positive charge. Now what happens? Now we can do the elimination or another rearrangement. Why would we likely or be better to do the rearrangement? That's actually why we don't have to stress here and just do the elimination straight here. Why is it better to show the rearrangement? And I see it, Dana. I'll come back to you in just a second. Secondary versus tertiary, which is more stable? Tertiary, which is more likely to form. The tertiary, we'd probably see another rearrangement before the double bond formed. How fast is all that happening? Probably so fast we aren't going to be able to see the difference. Dana, what was your question?
No, I think we got it. I just was wondering where the hydrogen went. I got lost at that part, I guess.
Oh, these pieces on what's picking up those hydrogens? This is something that I do not specify. Anything remotely basic is picking up that hydrogen. Okay? To do an elimination reaction, what is typically also added, which I also left off this to not give hints away? Heat. What's typically breaking that hydrogen off? Heat. Okay? And we're having that H plus get picked up by something in solution. I think you'd mentioned the sulfate picking it up. I object to showing the sulfate pick up that hydrogen. Why would the sulfate be questionable picking up that hydrogen? What happens if HSO4 picks up an H? It becomes sulfuric acid, which is a strong acid, which by definition would shuttle it right back the other direction. So I don't like using sulfate or any strong conjugate base of a strong acid picking up hydrogens. I would never mark you wrong on it. I would just circle it and say, I don't like this.
So we thought it would happen because of the high concentrations and just would take a long time for it to happen.
It would probably take a while to happen. More than likely, what you would end up seeing is the terminal double bond first, okay? And the highest concentration, as you gave it more time, you would eventually make it to the internal. Okay. Last one. What happened? Type of reaction. I think I heard that. We have a substitution reaction. Okay. How do we see that substitution? 1, 2, 3, 4, 5 carbons, which is 1, 2, 3, 4, 5. And I have 1, 2, 3, 4, 5 carbons. Ooh, this is interesting. So I'm doing a substitution of that hydrogen, or 1, 2, 3, I have too many carbons there, for that carbon structure, right? Where did I get that carbon structure? From the reactant. How did I get it from the reactant? I have that strong acid, which can go through and protonate, giving me the good leaving group. Then what can happen? A second molecule of the alcohol can do a backside attack, kick out the leaving group. We'd have all those fun little carbons. Some base can come in again and remove that last hydrogen.
But we have to remove the acid and add a base to an acid.
What's that?
Aren't
We aren't adding a strong base. We're adding any kind of base. The other way that that hydrogen typically gets removed in what is known as the workup. When we go to lab, do we just add the reagents? That's the end of it. We add the reagents and say, whoop, there's my product. Done. No, what do? You mix and add a whole bunch of other stuff and extract and wash and recrystallize and all those extra steps. All those extra steps are ultimately neutralizing the reagents by adding a weak base. That weak base would neutralize the sulfuric acid and probably finalize that hydrogen. Why do we not add that in lecture? Because no one wants to mention that. Except, I guess, me. Questions about that? So that's our reagents for our acid activations. We're just looking at how the structures can change and what they end up doing. There are alternate activations that we can go through and do with our alcohol. Okay, what is a big added complication of these right out of the gate? What's that? Stereochemistry. None of the other reagents we looked at involve stereochemistry. Why? All of those other mechanisms followed under SN1 dynamics. What happens with these reagents? SN2. Okay? So we control the reaction a little bit better, which means they tend to be more useful reagents. Okay? Putting chloride in exchange of the OH. Okay? Notice this is a fun one. SOCl2 gets me chloride in exactly the same location as the OH, but it also gets me in the opposite location. What's the difference? PYR, which is pyridine. Pyridine is why we end up seeing the stereochemistry change. You don't have pyridine, what happens? You get retention of stereochemistry. You add pyridine, you get inversion. Okay? So being very cognizant of the conditions can help you identify these things. In the other one, we're taking tosyl chloride and reacting with the alcohol. All we're doing is replacing the chloride with that oxygen. Right? Anybody know what TS stands for? That was a bad question because I just said it. Okay. Tosyl. What does tosyl look like? That's a little bit more difficult. We'll look at that in a second. PXR. What is PXR? What is X? Halides. Okay. And in particular, bromide and chloride. Okay. What is P? Phosphorus. Okay, we're using a phosphorus halide. That will end up with an inversion of stereochemistry as well. Okay? And these are all good because we're looking at SN2, but it's not necessarily because of SN2, it's because selective. In our SN1, we ended up with 2 products. In our SN2, we end up with 1. So these are good reagents because that SN2 is now selective. We get one product favored over the other. Okay? So thionyl chloride, okay, stinks to high heaven, by the way. It's awful. And so we have that cool chem, which we've already kind of alluded to. We can change the stereochemistry output. So there's our 2 reagents, our alcohol and our thionyl chloride. What do you see? Probably see 6'4", 230-pound guy staring at you blankly. Welcome to my life.
There's a potential substitution.
Okay, what do you mean?
You have I think I was going in there with so we could get the
When we look at our reagents, what should we be looking for? Reactivity. Ideally, source of electrons and someplace missing electrons. Does chloride typically have electrons on it? No lone pairs shown. Does oxygen typically have lone pairs or extra electrons? Does that oxygen have lone pairs shown? One does and one doesn't. Where's my source of electrons? Probably our oxygen with electrons is the one that's going to act as our nucleophile. So that's going to be our negative. Okay? And we can address questions on why that's going to be our source of electrons. Okay? But that is our source. What does that mean we then need to find? A positive. Why is there a partial positive on the sulfur?
Because the negative is going to go to the oxygen. And there's negatives on the chlorine, so all of that electron density is going away from the sulfur.
Yes, but you didn't use the key word I wanted to hear.
Resonance.
No, well, shoot, yes. Resonance was in there with the resonance pushing out onto that oxygen. Chloride and oxygen both have something in common, particularly in relationship to sulfur. Yes, they both have lone pairs. Electronegativity. They're both more electronegative than sulfur, which means if we look at the electrons around sulfur, where are they spending most of their time? Away from sulfur, making the sulfur positive. There's our reactive site. This is a trickier reaction for you. Right? Is this a substitution? In a strict substitution, we only exchange sigma bonds. Have we exchanged just sigma bonds here? No, we broke a pi bond. Okay? So that would suggest then an addition. Okay? But in the addition, what does the pi bond act as that we've seen so far? The nucleophile. Is the pi bond acting as a nucleophile? No, so this is a modified version of the addition we've been looking at. We've looked at electrophilic additions. This is actually nucleophilic addition, because I'm taking a nucleophile and adding it to a pi bond. Okay? This is what the whole next unit is talking or looking at. So it's a little bit more complicated of a mechanism. Actually, do I have this stepwise? That'd be nice. Okay. So we've done, shoot, I didn't do it nice and stepwise. The end result is that we break that pi bond. The pi bond being a negative charge needs to get stabilized. We shuttle the electrons back down, but then we'd have to kick something out. What do we kick out? Chloride, because
It's happy that way. It's stable.
why would chloride hold the negative charge better than the oxygen?
It's more electronegative.
Chloride is more electronegative and it's bigger. Okay? Why do we break the pi bond first instead of breaking the chloride immediately? I mean, we break the pi bond, then form it again.
Because you need to break the pi bond in order to show electrons from the oxygen to sulfur, which is without the chlorine.
Why did I not just do this? Why did I also include these extra arrows? Which bond is weaker, pi or sigma? Pi. What's my mechanism supposed to show? How my electrons react. I will break the pi bond first, forming a negatively charged oxygen, which is not particularly stable. I stabilize that negatively charged oxygen by immediately shuttling the electrons back down into a pi bond and pushing them out onto the chloride. Okay? It is a nuanced version of what's going on, but this is usually the shortcut for it. Yes?
So is it a concerted step and creates kind of like a ring structure-ish?
No real ring is actually forming here, connecting things, at least under these conditions.
Okay.
But that's how it ends up putting together. We kind of do all those things at the same instant. Okay? What do we now have within this structure? Positive oxygen. Does the oxygen want to be positive? No, so what happens? So our oxygen could take electrons from the carbon, but then that starts to push carbocation. So that didn't happen here. Pyridine will take the electrons away from the hydrogen. Okay, and we form a pseudo-stable intermediate. Yeah, there it is. Okay, now what happens? Backside attack, kicking out our structure, and we end up with our inversion. Oh, never mind, I didn't say that. Pretend I didn't say that. What happened to the stereochemistry? We get inversion in stereochemistry if we had it. Remember, I'm showing generic structures.
I thought that with the, oh no, sorry, I flipped it in my head.
So if we go back one slide, which is harder said than done, with pyridine, we get inversion. Without pyridine, we don't get inversion. Okay? Typically, you see it with inversion. Okay? So, go ahead.
If you add pyridine, what would that do then to that hydrogen?
So if there's no pyridine, what can stabilize that hydrogen?
Or none?
Actually, because I've got this drawn somewhere. Let's see. That's what happens. This is the cool chemistry.
Yeah, that's
Okay.
what I was asking about. If it was kind of
Oh, yeah.
without pyridine.
When you get rid of the pyridine, the oxygen needs to get electrons. It'll steal it from the carbon. Why does the chloride not come in? The other one, the chloride wasn't a super good nucleophile, okay? And this species doesn't make it electrophilic enough. So what ends up happening is the chloride immediately comes down and swaps out right away. We kick out the oxygen. Well, we said, well, that is kind of complicated looking. Why would it happen that way? What does it produce? SO2, which happens to be a gas. What do gases do? Leave. Can the reaction reverse when we don't have the reagent? No. Okay, sorry for breathing on you guys.
Oh, you can try and pronounce something.
Okay. So that's kind of the cool chemistry with ethynyl chloride. The other thing that's really neat with it is it works with all OH functionalities. Okay, what do we mean by that? What type of OH do we have right now working with? An alcohol. Okay, primary, secondary, tertiary, this reagent will work with it. Okay, it has a little bit of problems with tertiary. Why might it have problems with tertiary? Sterics. Okay. What's the other OH functionality? Carboxylic acids. Thionyl chloride will do the exact same thing to carboxylic acids and turn them into what is known as the... Anybody? Maybe it'll help if I draw it. So if we started with a carboxylic acid.
Acid chloride?
I will actually accept our acid chloride, but I'd go with acyl chlorides, okay, which will become really important in Unit 3. Okay? So we're looking at these reagents and what we can do with them and slowly build. Okay? And all of this kind of settles on that pyridine. Okay? Why is pyridine so helpful? It has that lone pair. It can do a substitution, making that group so large that it prevents the immediate substitution. It has to do a backside attack. Okay? So if we remember from that previous slide, if it pops up there, yep. We've got this structure. What is special about that structure? Well, it still has a positively charged sulfur. What could attack that positively charged sulfur? Pyridine. The lone pair on the pyridine. Okay, kicking out the chloride, which could get us that big, bulky, nasty looking thing. Okay, with it being so big, bulky, and nasty, the only way the chloride can come in and attack is by backside. We will necessarily get inversion. So that's what the pyridine is doing in this case. Okay. I have seen questions both directions, with pyridine and without pyridine. Okay, so be a little bit careful on just saying SOCl2 will give you inversion always. Okay. Very commonly, yes, but not always. Okay. The phosphorus activation, super exciting. What do you see in this one?
Lone pairs on the phosphorus, lone pairs on the oxygen.
Lone pairs on the phosphorus and lone pairs on the oxygen. What a jerk. Supplied electrons in both locations. Okay, which of those would we expect to be more likely to share electrons? Why? It's more electronegative. Electronegativity is the definition of holding bonding electrons, so I don't like that answer. Okay, so we might say phosphorus because it's lower in electronegativity. Yet oxygen is the one doing it here. Why would the oxygen be the one doing it? Is this just phosphorus? There's a little bit of sterics, but what else is there? What can you tell me about bromine? It's electronegative, which means what happened to the electrons on the phosphorus? They are sucked into the structure. The phosphorus ends up carrying a relatively high partial positive charge due to the halogens located around it. Okay? And much the same way that our sulfur in the previous case. So what ends up happening? The oxygen donates electrons and kicks out a bromine. Okay. What happens then? What's now floating around in solution? Bromide. Can backside attack. And we end up with our final product, okay, with the inversion in stereochemistry. What happens if instead of PBr3 I did PCl3? Same thing. Okay? Exact same functionality. Yes?
Even with chlorine not being a good nucleophile?
Yep. Even with chlorine not being a good nucleophile. Okay. What type of reaction? Substitution. Okay. What about that first step? That was still substitution. So it is a little different from our thionyl chloride. Our first step is still a straight substitution reaction. Okay? As far as mechanism, less than 3. We said it was substitution, so it would be S and 2. Okay? Just like the thionyl chloride works with our carboxylic acids as well. Okay. Last one we'll talk about, which we'll end with today, our tosylate activation. So there's our tosyl group. Okay, the TS represents this big old piece. That squiggly just means the structure continues from there. Okay. If that squiggle is an OH, then what would we expect that compound to be? Kind of except an alcohol. We have an OH, so it's not really a hydroxy. We really need to be next to a carbon for it to be an alcohol. Okay. What if we kind of blurred our view and forgot about that half of the structure? What does that look like? Sulfuric acid. Guess what the tosylate structure is with that OH? It's an acid. Okay, it's a really strong acid. Why would we use this as an acid instead of sulfuric acid? No, sulfuric acid has how much organic component? 0. Okay, it's just H2SO4, which means its solubility or organic compound solubility in sulfuric acid, just dissolving, pretty limited. Why would tosyl or the toluene sulfonic acid be better? It has an organic component that will help dissolve our organic species and help do the acid-base reaction. What if instead of an OH, we had chloride? Now what does it look like? Particularly if, again, we ignored half that structure. It looks kind of like our thionyl chloride. We have an active, I mean, it's not perfect, but it's close. We have a pretty good electrophile there. That sulfur is positive. So what can happen? Lone pair from our oxygen can come in and share, sorry, I get most of that structure back, with our chloride, kicking out the chloride, and we would end up with, let's see, I did not draw it. We would end up with this big old massive structure. And what is special about this now big old massive structure? It is a phenomenal leaving group because that is a stupidly weak conjugate base because its conjugate acid was a very strong sulfuric acid. So it's a great, great leaving group. Why does this reagent typically get used? Okay, if I now try to run substitution, I'm not doing inversion a whole bunch. The next step will get me inversion, but if I'd done the other ones and done 2 substitutions, I would have inverted twice. Okay? So this does not change the stereochemistry about the carbon because what did I do to the chemistry about the carbon? Nothing. All the chemistry happened out to the oxygen. Kind of makes sense? Okay. I apologize because I talked too long. Fairly standard. But there's our big summary of all of our reactions, and we'll probably move into a little bit more specific